Good afternoon, everyone. Welcome to the first workshop that we have today with respect to using AI for drug design and drug discovery. For these work sessions that we are going to have, essentially, it's gonna happen every Saturday from the same time that we have, from three to 4 p.m. These sessions are going to run from today, which is going to be July the 20th, all the way to August 24th. Each Saturday, we just meet and we are just going to work some kind of a workshop that in these sessions, we try to use generative models in AI in order to predict the structure of a drug or exogenous molecules that they can have therapeutic, I should say, benefits. That's why we are just going to call them drugs. In order to do so, these workshops that we are just going to run, we have some materials which is created on the Jupyter notebooks. The language that we use in order to run these generative methods is written in Python with the Keras library. And these codes, they are accessible on the school's website, which is also the GitHub account. Now, most of the materials that we use, they are collected from different resources. And these workshops essentially are walking through the most of the jobs that has been done, most of the algorithms by other research groups. We assemble them together. We just work through them to see how we can just extend them to the new molecules design. Now, these sessions also is going to be recorded, and the recorded materials are accessible through the YouTube account and also the website of the school for convenience of the participants and those people who miss to participate on a specific session that they can have the access to that on future dates. Then also during the presentation, if there is any questions rises, please put that on the question and answer section. Then it's just going to be answered as we move along. Now, I'm just going to share the screen with the notebooks that we're just going to use today. Now, okay, now I'm just going to walk you through for today, which is going to be the first session. The overall goal for today is that we are just going to walk you through what is the overall design of the things that we want to do, what kind of a generative algorithms we are just going to develop, and what are the fundamentals as an inputs for our algorithm is going to be. Because the problem that we have when it comes to drug design using the AI, the problem that normally you're just encountering with the training is that the molecules, they are just a kind of a discrete entities. For example, if you look at, for example, the structures as a functional group, at the basis of the functional groups, for example, the phenyl, which is a very important functional groups with the hydroxyl group attached to the benzene ring, then the thing is that the first thing that we're just going to ask ourselves is that, okay, I have a kind of representation of the molecules, which is a kind of a discrete entity. We have a phenyl functional group either on its own or attached to a part of the other carbon structures. Then the question that we're just going to ask ourselves is that, okay, how can it represent a data for the algorithm which it recognizes the inputs into the vector space in terms of the numerical vectors? Then that's the obvious thing that any AI enthusiasts, they know that if you are just going to train a system An algorithm, your input, cannot be a symbol, a molecule, or a discrete entity. First, you have to represent that and transform it into a numerical vectors into the vector space. And then you can train the algorithm. That's what we are going to do. But the problem, as you can see, when it comes to using generative methods for the AI, is that we are not working with the numerical method, numerical vectors initially. Then now there is a very important step when it comes to drug design and drug development using the AI. A very important step is that we represent them into a numerical vectors, into the vector space. Now, in order to do that, we have two strategies to make. One of those strategies, we are just going to use it today. And the second one, we are just going to deal with that in another workshop. The first strategy is that we are just going to use molecules or drugs. We are just representing them as a kind of, I should say, a kind of a graph. We use a representation, which we're just going to call that, as you can see, SMILES, which stands for Simplified Molecular Inputs Line Entry System. By using that, then we are just looking at the molecules, like the graph. Then in that sense, the atoms, they represent the nodes of the graph, and the bonds between the adjacent atoms represents the vertices of the graph. Then what we're going to do in that case, then we are just going to represent that graph in a form of adjacency matrix, which we're just going to see that which atoms are connected together through how many bonds. For example, if you have, for example, in the case of a molecule, which two atoms, like the solenoid, that they are connected, there's a connection between the carbon and the nitrogen, then if it just represents the adjacency matrix for that structure, which is going to be a 2x2 matrices, you're going to see that the connection between the CN, between the carbon and the nitrogen, is going to represent 3. And for that case, because we do not have a directed graph, we do not define the direction between the bonds that exist between the carbon and the nitrogen. In that sense, we're going to say, okay, it's going to be an undirected graph representing that molecules, then it's going to be a symmetric adjacency matrix, which is obvious. The number of the bonds between the carbon and nitrogen is essentially the same thing as the number of the bonds which is between the nitrogen and carbon. Then they're just going to represent a symmetric matrix through the graphical representation of the molecule, which first has been transformed to a conventional representation, which we just call them SMILES. Stands for Simplified Molecular Input Line Entry System. Now, then that's the thing that we're going to work with. Then for this workshop, what we're going to do is not essentially working with the phenyl groups, but phenyl groups first is going to be transformed into a representation, which is called the SMILES. Then from SMILES, we're looking into the graphical numerization of that molecular symbol that we're going to create. That is going to be the first thing that we're going to discuss. Now, for the purpose of these workshops, as you can see, and I have it on the Jupyter notebooks, which is there, the important thing that we are just going to work is we are just going to work extensively with the autoencoders. I'm just going to, for the sake of simplicity of what is going to follow, I'm just going to represent and discuss about what is autoencoders in just a couple of seconds, how it just can be adapted to what we are going to do, and how we can generate new molecules from the existing molecules data sets that we have from the autoencoders. And the first picture that you can see on this Jupyter notebooks, which is also accessible by the GitHub that we have on the school website, You see that we have a representation. We have an encoder section, we have a decoder section, and in between, we just call that latent space. For the people who have worked with the variational autoencoders or autoencoders, some of these concepts looks repetitive, but for the people who haven't just worked with these concepts, we just have a very simple introduction to that. Using those kind of concepts, you're just going to use that extensively as we work along the coming weeks. Now, what is the benefits of autoencoders? The autoencoders, as you can see, there are two stacks of the neural networks. The first one, that you are just going to feed the features of your input data. It's just going to reduce the dimension. It goes smaller, smaller, smaller. Then it reaches a bottleneck. That's what we call that the latent representation of the input data. Because there are the parts of the data which are not immediately observable. When you have the data at your desk, for example, you do not observe this type of the data directly from that. Now, that's what we call that latent representation of the data sets. Then at the bottleneck, again, you just move to the decoder on the right side. You see that that's the opposite direction. The stacks size is going to gradually and symmetrically, with respect to the encoder, are just going to increase that it reaches to the output of the data, of the model. But what is the benefits of that? The benefits is that when you, for example, when you have your own data sets, when you feed them into the stacks of the layers of the autoencoders, the encoders before introduce the bottleneck, because there is fewer numbers of the neurons representing the number of the features. For example, you remember if you had followed the previous workshop that we had when we talked about the perceptron, you remember, for example, with the perceptron or each neuron, essentially, what did we say was that we're looking to them as, for example, a kind of physiological neurons. The stimuli, the external stimuli that induces the ion voltage gated ion channels to induce the graded signals that if it reaches to the threshold to fire, for that case, each feature is going to be one input to each dendrites. Then imagine if you have a huge data sets which is going to represent like the external stimuli, like the physiological neurons that we have. And each dendrite is going to be recipient of one feature. If you put everything at once to the biggest layers in terms of the size and dimension, as you just reducing the dimensions, you are just like the pruning of the neurons, you are just selecting the right features representing the data sets. Then you become selective. Then when you get to the bottleneck, which is we call that the latent space, you just have the most effective features representing the data, which is not immediately observable when you have the data set itself. That becomes very important. For example, then you can just do the clustering on it. You can do many different algorithms on the latent space, which represents the latent observables of the original data sets. That's what it does. Then in a nutshell, the autoencoders, that's how it works. The variational autoencoders, it's the probabilistic version of the autoencoders. Then at the latent space, you do not look at the latent representation of the features as a single numerical value, but when you're working with the variational autoencoders, you are looking at the latent representation of the latent space of the real data sets in terms of the probability distribution. That's how it becomes variational autoencoders, which we're just going to work with that extensively for the purpose of our program. Now, speaking of this, later we just move on to the second part. The second part, which is taken from the papers, which is cited below that picture, is this. It shows the protocol of what we are going to do with this representation. Now, what does it mean? For example, we are just working with the autoencoders. For example, look at the picture A. At the picture A, you see, for example, you see the benzene ring. The benzene ring, we are not just going to use that directly in order as a kind of an inputs for our autoencoders to extract the latent representation of it. But what we are going to do, because it is very interesting, because look at that. We are sending a very important functional groups, benzene, for example, to the neural networks, autoencoders. But what is going to be represented from that input into the latent space, it's not going to be probably the benzene ring itself. That's how we're just going to do that. And essentially what we're going to see also later is that the latent space representation of the latent observables of the original data sets, every part of it is not going to be a meaningful part for the decoders. Then that's, we are going to see that later. That's how we are just going to put a regularizer into that. We're just going to put a regularizer into that. Now, in order to make sense that every part of the latent space be represented to a meaningful chemical structure. Now, then you see that, for example, the functional groups of the drug is going to be represented and transformed into the SMILES configuration. Then as you're going to see that through the numerical representation of the SMILES, we are just going to feed that into those numerical values in the vector space into the encoder neural networks. Then you see something in between. We have a continuous representation of the same molecule. Because you remember, the thing that I discussed was that when you have the molecular structure, the benzene ring, for example, a functional group parts of the drug, or the drug itself, it's a kind of a discrete data sets. But you do not need, and that causes a problem, because when it comes also to optimization, you need a continuous space representing the input data. Then if we just start with a discrete set, you cannot make a meaningful optimization on that. Then you see that the latent space that we create by doing some regularization techniques you're going to see later, it's going to be represented as a continuous space adaptable for optimization methods. And also you can see that from here at the decoder decodes from the continuous latent space representing the latent variables of the input drugs into again a SMILES configuration. Then that SMILES can also be visualized and reconstructed back into an organic molecules. Now, you see that also from the latent space, we create another latent space because we are just going to create from the latent space, the input from the latent space itself becomes the input entry to another neural networks in order to predict the chemical properties of the drug. For example, log P of the drugs, which we're just going to talk about that later. Then data space also to a different sense. Then what we're going to do for these algorithms, as you're going to see what's going to happen, is this: we make two ways prediction. One way, we predict the product itself. One way, we predict the properties of the product, the chemical and physical properties of that product. Like, for example, log P or lipophilicity, hydrophobicity, and those kind of stuff from analysis. Then, as you're going to see in these coming workshops, we are just going to have two different training, one for different, one for the SMILES, molecular representation, one for the physical or chemical properties. And also the picture on the right, which is going to be part B taken from that paper, it shows that our latent space is a continuous space That's why it allows you to do optimization technique. You see that from the latent space that we had, in the second network that we created in order to predict physical and chemical properties, we created a secondary latent space. You see that the one at the bottom, it's our original latent space, representing the latent observables of the original inputs. This latent space itself has been created, has been mapped into another, a secondary, but another continuous latent space for prediction of the drug's inputs. Now, these are essentially what we did so far. I just wanted to tell you how to uh, uh, familiarize you with the methods that we're going to do in the coming weeks. Now, in order to work with that, as I said, we are just working with the Python libraries Keras to create our neural networks. In order to do that, we need also some dependencies and some packages. The most important one is that we have to have installed the RDKit, which is a very important library and package for Python when it comes to drug design and chemoinformatics and computational chemistry. That's what we have installed. And Pila also, which is very important for visualizations of the chemical molecules and ligands that is just going to be generated through the generative AI that we're going to work with. Now, we have also some other libraries from RDKits. You see that, for example, we're just going to use, I'm just going to very briefly discuss what is the benefits of these different packages. We're just going to use a chemical package of the RDKit, which is very important when it comes to work. It gives you some functionality in order to manipulate and work with the molecules inside the IPE. The other thing that we need, it's important to discuss, it is Mo2Grid image. That what it does is that it creates a grid image of the molecular structures. Because remember, if you remember, like the convolutional neural network, you need to just do what? You're just working with the grids. And now you are pasting the molecular structures, which is a discrete entity, into a grid into our space. And that's what it does. Then that function from the RDKit library, it creates a grid that it puts the molecular structures into that space. And also the other packages is well established. Also, when it comes to using the drugs, to do the AI on the drugs, we need to start with an input data sets. The input data sets that we are just going to work with that, we just take it, we have two options to do. Either we use the raw data sets representing the molecules from the Zinc website, or we use that from the QM9 datasets, which this is a repository which is this represents the quantum mechanical, the quantum chemistry properties of the molecules, which they have been taken by dense computation. Now, and you can see that in the website to that molecule is there, which you can also click on it and extensively study that. You're going to see that you can find around 134,000 molecules with the properties that it ranges from the geometric properties. For example, you can see the atomic coordinates, the bond length, which these are very, or the angles between the bonds, which are elementary concepts in general chemistry. For example, the bond length, you see that, you remember from general chemistry, the bonds, as they stack on top of each other, the pi bonds is going to be shorter than the sigma bond. Atomic coordinates is so important to reconstruct that. And also the dipole moments, when there is a partial charges there, and homolumal gaps, which is a very important property of the molecules. And also you see that the thermodynamic properties, it's also measured when you use that data sets. For example, you're talking about the total energy or the entropy, which is a measure of chaotic structures of the molecule. These ones are also there. You can go to this website, quantummachine.org. As I said, you can find around 134,000 unique molecules, which normally they have up to 9 heavy atoms, including carbon, nitrogen, oxygen, and fluoride there. In order to extract the data sets, we read that data sets from the cloud, from the Amazon cloud. Now, when you do that, when you visualize the data sets that we are just going to start with, you see that the visualization of the molecule is this. Now, but from here, in order to go to the workshop and continue further with the generalization of the method, we need some fundamental knowledge and practices with working with the SMILES structures. Because look at that. With the molecules that we have structured here, it says that with the code which has been written, it prints the SMILES, and you can see that, okay, the SMILE structure is this carbon number 1, and you see that we have carbon, nitrogen, carbon, carbon at the 10th structure there. Now, and the number of the heavy atoms, this is going to be 7. Now, which includes maximum to 9. Now, but what we are going to do that, I'm just going to stop at this slide that we have right now and temporarily change the shared documents, the shared Jupyter notebook in order before, because the next thing that we're going to do with this, it goes to data preparation as an input for our autoencoders. But before that, the thing which is important is that I'm just going to walk you through to some basic and elementary SMILES representation of the atoms to just work with them to have an idea what can we do with them. Okay, now, when we just go there, we see the data sets over there. I'm just gonna work with the synthetic data in order just to demonstrate how to just work with the SMILES in Python environment. Now, you see that again, we have our popular libraries taken there. We have also again used the RDKit. We are just using the Chem library there, which gives some functionality to work and manipulate the molecular structures. Argyle Logger, it shows the messages. So each training part. We have IPython console from the ChemDraw and molds to grid image. They're all good for drawing the molecules. Alongside with this package, which is draw from RDKit Chem, we need the draw that essentially what it does, it's important to visualize at each step that we create a molecule. What you do is that we just start to visualize what we have created. And also descriptors. Descriptor, what is good, we can get the descriptors of from the Chem package of the RDKit. When we use the descriptors, we can just get additional information about the molecule that we have created. Now, for example, the boiling point as a physical property, it comes all with the descriptors functionality of the RDKit package. Now, the first line of the code, which I'm just going to walk you through, that what is that? Because in order to be able to work with the ML pipeline that we have prepared, it's important to know how to work with the SMILES and molecules in Python environment. Then, as I said before, this Jupyter Notebooks, which is also going to be shared in the school's website, which is going to be posted after the workshop, you're going to see that these lines are so important in order to succeed for the machine learning pipelines. Now, in these ones, I have from the RDKit, I have all chem. gives more functionality, descriptors, provides descriptions of the physical and chemical properties and drug, and also Pi3D mole, which is important for 3D visualizations of the molecules. Okay, for example, in terms of the SMILE, I create an object, and the object is going to be CCO. When it comes to the SMILE presentation, we know that you do not need to show the Lewis bounds between two adjacent carbons. On the carbon with the oxygen, you just break the bounds, you put them close together. But remember, this is the ethanol structures. The ethanol structure, if you remember, it comes with two carbon, with three hydrogen attached to the first carbon, and the carbons are connected together, two hydrogen attached to the second carbon, and it's all connected to the hydroxyl group. But you see that in the SMILE structures, on the first carbon and the second carbon, we do not show the hydrogen. Then I do not show CHO. The hydrogen, as this is also neglected to draw them on the molecular structures of organic chemistry, on the SMILE representation, hydrogen is implicitly represented, not explicitly. Then for the first part, as you can see, I have created an object. I call that a SMILE. It's an object which I create. It embeds CCO in a string. Now, in order, because CCO, in order that we have it there, in order to communicate with Python IPE, that what CCO means, we need to just use this function from the chem library of the RDKit, which is mole from SMILES. What does it do is this one. I'm creating a molecule because look at that, the CCO, it's so hard to convince your IDE that CCO is a representation, symbolic representation of ethanol alcohol. In order to do that, you have to just use this one, mole from SMILES. It means molecule from SMILES. Then whatever you have created here at the SMILES, if you just put this here with this function, molecules from SMILES, it creates the molecule structures for you. Now, if we just go also, we go to do some other operations. Now, for example, the molecules which I created now, the Python understands this molecule now as a molecule, organic molecule. Then now you can use another thing, which is called getNumAtoms. This is another function, comes from the RDKit. And what does it do is that the number of the atoms in the molecule is going to be created. For example, that's one. We're not going to work with that essentially too much, but that's a good thing when you just do the, for example, exploratory analysis on a molecule that you start to work with to see how many atoms it is constructed with. Now, the other one is that you see that we are using the descriptors, which is a package also with the molecule weight. What does it? It's MOLWT. What does it do? It's the function, a part of the functionality provided by the descriptors. As I said, the descriptors, they are providing the physical and chemical properties of the molecules. For example, if you put mole weight, part of the descriptors, it gives the weight of the molecule, which is the molecule weight of the molecule is the object that we created. The other parts that it comes, is essentially create visualization of this one. You see that we are just using the package draw. And we have also molecules to image. We have the molecule and we have other parameters set as true. And you see that also we have a 3D visualization. When you execute this code, you see you created two things. First, you have a double image, 2D space with ethanol. It opens in a different window. And also, you see the 3D image. It is this bond. It comes three. It's carbon with three hydrogen there. This intersection is another carbon with two hydrogen. And this red one is essentially hydroxyl functional group, which is for the alcohol's functional group is there. It's an interactive 3D dimension that you can do that. But at the same time, for these functions, we just noticed that the number of the atoms in the molecule is three. What does it mean the number of the molecules is three? It means that the type of the molecules is three. It doesn't mean the quantity, because quantity is more than three. You have three hydrogen here, two hydrogen here, five. You have one hydrogen here, it's six. You have two carbon, then it becomes eight. You have one hydrogen here for hydroxyl group becomes nine. You have oxygen becomes 10. But when it says that the number of the molecule is 10, the number of the atoms of the molecule is 10, it means that the number of the distinct type of the molecules in the drug or in the compound is 3. Because you see that in terms of the diversity of the atoms that you have there, you have the carbon, you have the hydrogen, and you have the oxygen. Then that's the reason you see that the number of the molecule is 3. Also, you see that the molecular weight of the molecule that we created is 46.069 units. Now, we just go to the next type of the functions and capabilities coming from the RD kit before we just delve into the workshop that we are doing. In this one, you see that I have created some parameters. For example, I said that the bound, for example, dim, which what does it mean? It means that the type of the bounds that you may have. For example, you may have a single bound, a double bound, triple bound, aromatic bound, and the one that we just put there is a kind of a it's a kind of a convention that you put one there as a kind of a buffer for padding, for example, that if you want to introduce another bound, that you can put it there. Number of the atoms, for example, is the parameter we define that the number of the atoms is going to be 9. As I said, the number of the atoms is 9. It doesn't mean that the population aspect of the number of the atoms. It means that we can have 9 distinct type of the atoms there. For example, from hydrogen to fluorine to chlorine, or let's say, for example, the carbon. Now, what we are just going to do is that we are just going to create an adjacency matrix. You are going to see that later in our workshop. What do we mean by the adjacency matrix? And also at the beginning of the workshop, I very briefly highlighted that. What is the adjacency matrix? As you can see, in order to find it, I'm just using the NumPy. I create a square matrix, which comes with this dimension, the type of number of the bounds, which is 5, and the number of the atoms, and the number of the atoms, which you see that in that case, we have this one, which is created, the adjacency matrix. Now, if you execute the line, you have created the adjacency matrix. You see that because we have 9 atoms and we're looking for the adjacency matrix to see that if any atoms are connected by one bound, we just put 1, 2 bounds, we put 2, 3 bounds, we put 3. You see that we have 9 elements on top, 9 elements on the bottom, and that's why you see that. Now, we go to the next one. For the next one, what we have done is this. What we wanted to do, we just get a feature matrix. Feature matrix is essentially, it's the property of the molecule that we're going to create. But how to do that? We have the number of the atoms, the maximum number of the atoms which are distinct. Atom dimensions, it refers to the number and the type of the bonds. Now, they have also the features. It's again coming from the NumPy, which is going to be the number of the atoms and the atom dimensions that we have there, and the atom index that we have created, because we just want to put an index to each atom. Then we just call the atoms not directly, but through the index. Then you see that atom type 0, which we said that if the carbon is there, we just start from the carbon, we put it 0. Or, for example, if the carbon is 0, then we can define it later, for example, for nitrogen to be 1. And we can execute the code to see what happened there. Now, we can go back to, as long as we just have some kind of a brief idea of how to work with the RDKit. I go back to the same notebooks that we had to just do some kind of to see what we have done before we just go deeper into the workshop with the pipeline of the autoencoders. Okay, the first thing that we did was this one. We said that with the parameters that we are going to define later, you see that I created kind of a dictionary, and I call that a mapping directory, a mapping dictionary. You see that I said that the atom mapping, that's the thing which we did before, because I just wanted to put an index to the atoms. I'm not going to call them because you remember on NLP also you have done the same thing. You assign numbers to the words and the frequency that those words are being repeated. And now when we are working with the molecules, even after we have transformed them into the SMILES representation, even after they are transformed into the SMILES representation, you see that we need a kind of a mechanism to assign numbers to the elements that they are not readable by the machine itself. Then in order to do that, we create a dictionary. For example, we can have a convention that carbon is going to be represented by 0. Then anywhere I called 0, it's a representation of the carbon. Also, the reverse is true, that the 0 is going to be carbon. Then conventionally, I can say nitrogen is indexed 1, or 1 is indexed nitrogen, vice versa. Oxygen is indexed 2, or 2 is indexed with the oxygen, fluorine with 3, or 3 as fluorine. This is a very important one. This is now we just do atom mapping in order to introduce numbers instead of elements. Now, the other thing that has been done here is that, for example, you see that the atom type is nitrogen. But we're just going to call the index, you see that we just put the nitrogen as 1 as a representation. You see that if you just put, for example, index for 2 is going to be oxygen. You see that when you start atom type, atom mapping, put the index as 2, you get the oxygen. For 1, you get the nitrogen as this is there. Now, the other thing that we are just going to do in the drug design workshop, we also, the number of the bonds between two elements is of critical importance. For example, the chemical and physical properties of a molecule that in a functional group has a single bond, a double bond, or triple bond is going to be very important. Now, for example, that's what we're going to do. If there is a single bond, we are just going to denote it by 0. Then I'm going to say, even if I have 0, I look into the chem library from the RDKit, and I put bond type SMILE 0 represents a single bond. The same thing for a pi bond, which we said that if we have 1, it represents a double bond. If this is 2, represents a triple bound. And if this is 3 as an index, it means an aromatic bound exists between two elements. Then now the other dictionary which we created, essentially what does it do is this one, that we just create some mappings in order that not to numerize the element symbols, but also index the number of the bounds. As I said, why? Because the number of the bounds gives distinct physical and chemical property. For example, if you have a double bound, a triple bound, you have a distinct and more rigidity to the structures besides from the chemical properties that is going to be induced for the molecule. Now, this is some kind of a exercise that we did. Double bound is by 1, triple is by 2. Now, I'm going to talk about the parameters. Then the next part of the workshop, we are just going to do that next week, as we are just going to talk in details of what each part of the code representing. Now, we have some parameters we decide. We said that the num atoms, it's the maximum number of the distinct elements in the structures. Then we are not going to design a molecule which is going to be so huge. Only the maximum type of the 9 elements in that molecule. Now, we said that atom dimensions, we have 5. This is the number of the atom types. We have bound dimensions, the type of the bounds that we create, as what we did before. And also, we have a latent dimension. This is essentially the number of the neurons that capture at the bottleneck of the latent space of the autoencoders. Now, speaking of which, at this stage, we are just going to finish the workshop before we just go to see more in depth how can we just create the inputs to the autoencoders. But what we did today was essentially, at this part of the workshop, what we did, we not only discussed the key structures, the key elements of discovery of the drugs by the AI and the importance of a vector numerization of the drugs first before any training is to start. And also the other thing that we discussed, we talk about very important, I should say, SMILES structures and how to work with the SMILES into Python and how to convert back the SMILES into the molecule and some methods for visualization. However, for next week that we discuss, when we're just going to start, we are going to talk about how to change the SMILES representation into a graph, because that's the plan that we have, and also how to convert the graph into the molecule. These are two important parts. The first part, we are gonna change SMILES into the graph, and that's going to be the plan that we had, because we said that then we have the SMILES, we have the molecule, we have to transform its representation into the SMILES. Then from the SMILES, it's going to represent a graph. Each element in that molecule represents a node in the graph, and the bounds between them represent the vertices of the graph. And that was the reason also we were very curious to index the number of the bounds and the type of the bounds. For example, sigma bounds is represented by 0, double bound by 1, triple bound by 2, and aromatic bound is going to be represented by 3. Then when we just represent the graph, that's going to be the input to this function, take care of the input for the encoder. But from the decoder, as an output, if you remember, we have to convert back the graphical inference that we make into the molecules. And that's the second function, is doing this. SMILES to graph, and graph to SMILES, and SMILES to graph. In order to see how these codes are written, plus more details on how to train the autoencoder as a generative AI For drug development and drug design, we're going to talk about that next week for the next workshop. We can finish that to more details.